I see a red light. I guess I'm on the air. Hi, boys and girls. My name is Butch. My full name is Terry David Silvercloud. You can search me later on. So I'm 74 years old. I'm not the least bit shy, but quite reclusive. So I live alone, and I'm old, and to keep myself busy, I work on my art most of the time. And I make videos to see if I can teach some of the humans out there a few of the things I know. So everything I tell you is what I know. You don't have to believe me. I encourage you to check everything out dozens of times. There's lots of bad information out there, especially in the world of science. Maybe science isn't in particular, but in the world of physics, which is the study of energy, matter, and motion, there's a lot of misunderstandings of a lot of things, and one of them is the word photon. So I'm a bit ADHD, and I tried to write down some of the things I'm going to try and cover here. But the word photon, I really don't like it at all. I think we got to blame Einstein for it. Anyhow, it's in common use in a couple of different ways. So the ways in which the word photon, you need to know where it's coming from, whether you're dealing with photometry, which is things like light meters and almost anything, in fact, which where electrons are generated somehow by light energy falling on whatever, as a way of measuring things so that everybody has a standard measure. And actually I'll read you out the definition of that while I'm on that before I forget. It's a unit of retinal illumination equal to the illumination from a surface having a brightness of 1 candle per square meter seen through a pupil area of 1 square millimeter. Notice it's square millimeter. So in the world of photometry, which is where you use light frequency energy waves that involve what you and I would consider to be light, there's a definition to make sure that people build their instruments the same way. That's a kind of an understood standard these days. And it's very handy to think of light seen on a particular area of surface area, because then we can measure this really nicely. And it doesn't really matter what color that surface is. What we're interested in is how much light is coming back at us, because if it isn't coming back at us, we can't measure it. So that's what light meters do. And it turns out, while I'm on it, before I forget about that, in the world of physics, or in the world of quantum physics, the elemental unit of reality separating the wavy-davy world of quantum here-ness and there-ness and the real solid particle world, the world of things that go bump in the night. The electron is the unit of choice, and it's the smallest solidy thing we know of. And if there were smaller things, and I firmly believe there are, I believe gamma rays are actual particles. It's just that they're much smaller than an electron, and I believe electrons are composed of gamma particles, but that's another story. I believe, let's get that out of the way, I believe electrons, they're all the same, we know that. I believe electrons are monopoles that can have left or right spin, and that they are shaped as icosahedrons, and they are composed of 20 tetrahedral shapes, which are gamma particles. So I got that out of the way. That's my opinion. Take it or leave it, I don't care. I'll be dead soon. That's why I make these videos. if I don't tell somebody these things who will know that I thought about them, and I can teach you a few things. So you want to know what a photon is. So in the world of quantum physics, the photon is the elemental photon. And one electron, if this is an electron, and this is a photon, these two, this thing here is not solid in this case. It can merge into there, and inside every one of these is one photon. You got that? So the thing is, an electron has a one quantum mass to speak of, and it contains the energy of one quantum, which is one photon. And why is that? Well, it has to do with the physical size of the electron, and physicists assume it's a sphere, and I'm not going to argue with that. Spinning icosahedrons are also spheres. Very, very good drill bits and fans too. Anyhow, where were I? So on my list of what I'm supposed to talk to you about is, because I lost track of what the hell I was talking about. That's what I was talking about. In the world of quantum physics, the photon is one quantum. Now here's the messy part of it all. There are photons, and then there are photons, and photons can be pretty much as big as you want them to be, and they aren't all the same photons. Oops, where'd that come from? Well, it's because of the nature of waves, and waves come in all shapes and sizes, but the standard size waves, which I wanted to get across to people, are normally called sine waves, which are nice roly-poly waves, sawtooth waves, which go up and then suddenly go down, suddenly go up, and these are just generalized shapes, and then the square wave, and you could have combinations of these things. Some sawtooth waves can be so vertical they just look like up and down lines, but they would be sawtooth waves. They go up like that, and they come down just as fast, just like today's pop stars. Here today, gone tomorrow. Andy Warhol's 15 minutes of fame for everybody. Where were I? Waves. So a photon is a particle with wave properties, and that comes about because what a photon actually is, I think I might have to uncover something here. No, I don't. Is that one wavelength, well, I can use this. Can you see this down here? Oh yeah, you can see this. Oh good. So you can see if this is a sine wave shape here. Don't worry about anything else written there. Just look at this wave shape. Listen to my voice. Listen care. I know how to hypnotize people. We won't get into that. Haven't done that for like 50 years. Anyhow, a wavelength is the distance between which, if you drew a wave out on a piece of paper like that, it went up in one direction, then back down to where it started without be halfway, and then the opposite way, and then back to where it started from. Now you could think of that. Remember our electron? Do you remember the electron? Well, if you thought about how long it took this hole to rotate and go all the way around there, that would be a frequency of 1. And if it did it at the speed of light, that would just be the way it were. It didn't mean the speed of light changed at all. It's just a very long wave that happened to be what we call 1 second. So this is what I'm going to try and get into your mind. Frequency is time. And how you view frequencies is how you view time. Your watches are all going, there's a crystal ticking away in there, and it's just counting the waves that this little crystal is kicking out. And so we measure time by the distance it takes one wavelength to happen. Now it turns out that a photon is directly related to the frequency of any given wave, and there are zillions of them, which is a good thing, it turns out, in a lot of ways, because it leads us to being able to analyze things with spectrometry, because in the visible realm, which our brains respond to, it turns out that green is somewhere in the middle, but very close to that, there's a thing, and I'm going to have to read this out to you. To get something electronic to work, if this was a photocell of some sort, and light, I just remembered something I forgot to talk about. I think the word photon came about a lot because when Einstein was doing relativity, he didn't know nothing much about waves at the time, and then he got into light, and I think that's how he came up with concentrating so much as a photon related to light. So there are light photons and there are quantum physics photons, and the quantum physics photons are the amount of oomph it would take to get this thing not to spin, but to move. One whole diameter. It could also make it spin one whole rotation, but for an electron to move, it don't want to go nowhere. It just wants to stay. Get away from me! It repels all other electrons. The electron hates all other electrons, like, get away from me! That's what's causing gravity, in my view, and electricity and everything, magnetism, the whole bit. These monopole electrons, in spite of their spin, whatever spin they go with, repel other electrons. If they come upon one with opposite spin, they can form what are called electrons pairs, where they both sort of put their feet at the same point of spin in space, and one thinks it's turning left and the other thinks it's turning right, and they're just sharing a common pole here in the middle, which is a common point of rest, so they can use less energy. That's why they unite themselves. How did I go? I'm ADHD. A photon. So a photon depends on what you're talking about. So in quantum physics, it's one quantum of energy, and energy is measured by a number which a physicist named, was it Joseph? Or losing first. Planck came up with, and the number's been juggled a few times, and I hope I have the correct one. Every now and then people get even better measurements, but we can measure it pretty quickly now. And Planck's constant is 6.626070040 times 10 to the minus 34. So if you could think of 10 and you put a comma there and you put 34 more zeros out there and divide it into 1, it's really small. So when you get back to your electron, your basic electron just sitting there in space minding its own business, it possesses a Planck's, whereas you have to assume that somehow, either with the diameter or the circumference of the electron, that Planck's constant is directly related to the electron, because it is the elemental unit that we use for everything. To see, to smell, in physics, quantum physics, all science, your eyes and brain, and nothing would work without an electron. So these are the little workhorses of the universe, and where were I? So the smallest wave you can have would be related to the electron, either by how fast it was spinning. The faster, it can just sit there and spin faster and faster and faster. But there will get to be a point where it'll say, I'm out of here. That point is where it has absorbed so much energy, wherever it is in whatever atom it's in, it wants to shift its orbit. And if it's in the outer one, it literally jumps out of the atom into space. It may come back, and it probably does really quickly, but it says, I'm out of here, screw you, I'm out of here, enough with the spinning. And we know that the particular amount of energy of the quantum physicist's quantum units it takes to make it do that. And when you do the mumbo jumbo math, it turns out that it would be a wave that was 683 nanometers long. That's way the F bigger than the size of an electron. Way bigger. But that's a lot of energy, and what it means is some sort of bully came along, and here's our poor little electron, and this thing said, out of the way, you. And the electron said, yes, sir, and backed off. And it bounced right out. It was part of the atomic surface of this surface, and it just jumped. It said, yes, sir, and it leaped right out of the atom it was in and said, yes, sir, I'm out of here. And the size difference, this isn't a very big size difference, but the size difference it would take to do that in terms of the actual little quantum physicist photon to a light photon, this is where it gets messy, see, would be a light photon would have a wavelength in a frequency that had a wavelength 683 nanometers, and using that with the Planck relationship, it would have an energy, that wave would have an energy of 1.82 electron volts. You don't have to worry what that means, but that's just, we can measure it. So how much energy, like how many photons, how many quantum physicist photons per second at the same time, not just one after the other, like dump truck, like that would it take to make the electron say, yes sir, I'm out of here. And it would be 1.82 electron volts, and that's what happens when light meters are working, or things that, your cells that generate electricity, those electrons get captured cleverly, and you ain't going back, kid, we got plans for you, you're going to the battery. You're going to the battery jailhouse until we need you. Where were I? So did I talk about Planck's constant? What I wanted to get across to you is the big thing with photons is that photons can be as big as you want. It is the energy of any particular frequency. Now here's the tricky thing with waves. The longer the wavelength, the stronger it is. The problem is it takes a long time for it to use that up. So if you want the job done like dynamite or C4 explosive, you want really short waves. With explosives, that's done by combining chemicals that they really got the hots for each other, and they're not going to waste time doing it. There's an association of the higher the frequency, the more energy the wave has. That's because it takes more energy to compress the energy into a shorter frequency. Are you getting what I'm talking about? So if this is a red wave between my arms, the wavelength, where am I? That way. There we go. There you are. You gotta look at the camera here. So if that was the wavelength of, between my hands was one red wavelength, that is much, much, much stronger than a single blue wave. But to make that blue wave, you've got to compress time and space, literally, to make it happen now. And it won't have a very big bang all by itself, because a photon is only a photon. It's only as big as it is. So what has to happen is the number of photons per second hitting something per unit of time is the frequency. I've really meandered off here. Where am I up to? 20 minutes. Easy talks, easy talks. You were probably confused, and that's why you came here, was to try and find out what a photon is, and you have every right to be confused. Photons are a difficult thing to keep in mind. Like if you were going to make a laser, you would want to make light start vibrate. If you wanted a green laser, say, you would want to make, let's make it a blue laser. The wavelength of blue light is 666 nanometers, roughly. A really nice blue. So you would want to generate photons, a frequency. You would want to generate blue photons. Are you getting it? There's photons can be as big as you want them to be, depending on whether you're just into elemental physics or quantum physics. So if you're dealing in quantum physics, you best be remembering what. A gravity wave, in theory, is its own photon. It's not light, but a photon is defined by the elemental unit, which is the electron. And anything bigger than, anything bigger generated by anything longer, like any wave that has a wavelength longer than the diameter of an electron, will be actually being defined by the number of electrons being detected per second and what the frequency is. Now, if it turns out that we're not detecting physical motion like electrical motion, we might detect radio motion. And it turns out when electrons start spinning faster than 100,000 times per second, they churn the space around them. They just said, okay, I got to disperse this energy somehow, and the way they do it is radio waves. When it's smaller than that, it's dispersed as basically gravity waves, which you'll call magnetism. But when the waves start getting up, and the frequencies past 100,000 cycles per second, the electrons are spinning. They have two choices: either make the antenna or the whatever they're in start getting really hot, like red hot, blue hot. They can jump into space around them to try and escape literally into the air, if it's on the ground here like a microphone. Or they start churning the dark matter and dark energy all around them to disperse the energy not as heat, but as ultra high frequency waves. So have I drifted off? Have I confused you enough yet? Don't be discouraged if you find the term photon confusing. I suggest, for the purposes of physics, that you always think of a photon as being the elemental charge of an electron. There's another measurement, which is how much energy an electron would require to jump out of its orbit, and that's basically covered by the same thing I was talking about, is what the 683 nanometer wave, what that would be. What I didn't mention is that 683 nanometers is infrared, and just beyond infrared is heat. So infrared will cause electrons to jump out of their orbits, and you can imagine if they can't go anywhere else, the actual substance will start to heat up, because actual heat will start to be generated. Heat is around 900 to 1,000 nanometers, which is 1 micron, which, while we're in the business of 1 micron, the entire spectrum of light is 1 micron. And it turns out the rods and cones in your eyes, that's how long they are. That's so that they have antenna long enough to vibrate with the longest red waves and still catch the blue waves down here in the tip. And the blue waves the red waves take a while to arrive, and the blue waves will be jiggling the tip there. So I've drawn out here a single red wave, which is 666 nanometers, which is 0.666 microns. Did I cover everything? Time is frequency. You can use photons to measure time, but it's hard to do because it's the same thing as using electrons, and we do already. Amplitude is photons per second. You can't increase the brightness except by hitting the same spot at the same time with more photons per unit of time. It takes more energy to make a short wave than a long wave, but long waves have more useful energy. A tsunami, which is a really, really, really long wave, you're wiped out. So if a little tiny little short wave slaps you on the beach, you don't think much of it. If that little short wave on the beach were 200 feet tall when it hit you, you might be a bit concerned, but it probably wouldn't be. It can happen. So I've gone on and on and on and on and on. A photon is a unit of energy and is directly related to electromagnetic frequency, and the light photon that people mostly associate with light has an energy which would be associated with a infrared wave, in spite of the fact that the elemental photon, the electron, is much, 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 much smaller. And the size of the elemental electron is somehow directly related to Planck's constant, because the smallest unit you can have is an electron with no spin, and the only way you can measure an electron smaller than that is by measuring either how fast it isn't spinning or how fast it is spinning. But you can also measure how fast it physically moves. I said enough. I better go. So anyhow, I believe electrons are the smallest physical particle, and there are more electrons than there are protons and neutrons. And the reason I can say that is you can eliminate all the neutrons immediately, because every neutron is one proton plus one electron. So that immediately nullifies every single neutron there is. So it becomes all the other electrons versus the protons in the universe. And my suspicion is their energy balance is pretty good, but it never balances out, and it never will, because electrons are monopoles and they cause gravity, which is push, not pull. If you think about it, don't believe me, gravity is push, not pull. Get over it. It's the same thing. The math works out the same. But once you start thinking of it as push, not pull, you will realize, oh yeah, now everything makes sense. It made sense to me quite a while ago, but I'm into physics. Terry David Silvercloud, 74-year-old motor mouth, spread the word. Go watch Butchie Poo in Vancouver. So I'm going to shut up now. It's a nice sunny day here in, 6th of November 2018 in Vancouver. It's a nice sunny day. Bye from Butch. Oops, there's the button. Where is it? There it is.